Welcome, curious minds, to a journey back in time, to an era where the universe still held countless secrets, and the very fabric of reality was about to be rewoven by a single extraordinary intellect. We're talking, of course, about Sir Isaac Newton, a name synonymous with genius, discovery, and a revolution in scientific thought that echoes to this very day. Born in 1642, a year that tragically saw the death of Galileo Galilei, it almost feels as though the torch of scientific inquiry was passed from one titan to another. Newton's early life was far from auspicious. Born prematurely in Woolsthorpe, Lincolnshire, England, his father had passed away 3 months before his birth, and his mother remarried when he was 3, leaving him in the care of his grandmother. This early solitude, however, may have inadvertently fostered the deep introspection and self-reliance that would become hallmarks of his later scientific pursuits. His early education was somewhat unremarkable, initially earmarked for farming, a path he distinctly disliked. It was his uncle and the master of the King's School, Grantham, who recognized his intellectual spark and persuaded his mother to allow him to pursue further studies. In 1661, at the age of 19, Newton entered Trinity College, Cambridge. He enrolled as a sizar, meaning he performed various menial tasks to pay for his education. This period was crucial for his intellectual development, as he delved into the works of Descartes, Euclid, and Kepler, laying a robust foundation in mathematics and natural philosophy. The established curriculum, largely Aristotelian, began to feel outdated to the burgeoning mind of Newton, who was already charting his own course of study, driven by an insatiable curiosity about the mechanics of the natural world. He was not just absorbing knowledge, he was questioning it, dissecting it, and preparing to build an entirely new framework. The world was about to receive a profound update, thanks to the quiet, determined young man from Woolsthorpe. The plague years, a crucible of creativity. Imagine a time when a global pandemic forced the world to slow down, compelling individuals into isolation. Sound familiar? For Isaac Newton, the Great Plague of London in 1665 and its subsequent outbreaks proved to be a period of unprecedented intellectual explosion. Cambridge University, like many institutions, closed its doors, sending students and faculty home to avoid the contagion. Newton, then a young scholar, retreated to his family estate in Woolsthorpe. This forced sabbatical, often referred to as his annus mirabilis, or year of wonders, was anything but a break. Instead, it became a fertile ground for some of the most groundbreaking ideas in the history of science. During these 2 years, from 1665 to 1666, Newton, free from academic obligations and distractions, dedicated himself to intense study and experimentation. It was here, in the quiet solitude of his childhood home, that he laid the foundations for calculus, formulated his theories on optics, and most famously, began to develop his understanding of universal gravitation. The legendary apple falling from a tree, while perhaps apocryphal in its dramatic simplicity, encapsulates the spirit of profound observation that characterized his work during this period. He wasn't just seeing an apple fall. He was questioning why it fell, and if the same force that pulled the apple to the earth also governed the motion of the moon around the earth and the planets around the sun. This period of intense, solitary thought underscores a powerful lesson. Sometimes the greatest leaps in understanding occur not amidst the hustle and bustle of daily life, but in moments of quiet contemplation, when the mind is truly free to wander, question, and connect seemingly disparate phenomena. The plague, a devastating force for humanity, inadvertently provided the crucible in which Newton forged the tools that would unlock the universe. The language of the universe, calculus unleashed. Before Newton, describing continuous change was like trying to catch water with a sieve. How do you quantify something constantly in flux? How do you calculate the instantaneous speed of a falling object or the rate at which a planet's orbit changes curvature? The existing mathematical tools simply weren't equipped for such dynamic challenges. Enter calculus, a revolutionary mathematical framework independently developed by both Isaac Newton and Gottfried Wilhelm Leibniz. While the priority dispute between them was a heated affair, it is Newton's approach, known as fluxions, that underpins much of our modern understanding. Calculus, at its core, provides the means to analyze and understand change. It's divided into two main branches, differential calculus and integral calculus. Differential calculus deals with rates of change and slopes of curves. Imagine a car accelerating. Differential calculus allows us to determine its exact speed at any given moment, even if that speed is constantly changing. It helps us understand how quantities respond to infinitesimal changes in other quantities. Integral calculus, on the other hand, deals with accumulation of quantities and areas under curves. If you know the car's speed at every moment, integral calculus allows you to calculate the total distance it traveled. These concepts, seemingly abstract, are the backbone of virtually every scientific and engineering discipline today. From predicting weather patterns and designing bridges, to understanding the flow of electric currents and modeling population growth, calculus provides the essential language for describing and predicting phenomena in a world where nothing is truly static. Without Newton's profound insights into this mathematical domain, our ability to understand and manipulate the physical world would be drastically limited. The prismatic revelation, the nature of light. For centuries, the nature of light was a profound mystery. Was it a stream of particles? A wave? How did colors arise? It was commonly believed that prisms added color to light, or somehow altered it. Isaac Newton, through a series of meticulous and ingenious experiments, shattered these preconceptions and fundamentally reshaped our understanding of light and color. His key insight came from passing a beam of sunlight through a prism, observing that it fanned out into a spectrum of colors: red, orange, yellow, green, blue, indigo, and violet. But Newton didn't stop there. He then took a single color from that spectrum, say red light, and passed it through a second prism. If the prism was adding color, he reasoned, then the red light should be further dispersed. But it wasn't. The red light remained red. This led him to the groundbreaking conclusion that white light is not pure, but is in fact a composite of all the colors of the rainbow, and the prism merely separates these constituent colors based on their different angles of refraction. He also demonstrated that these individual colors could be recombined by a second inverted prism to form white light again. This revolutionary discovery, detailed in his seminal work Optics, published in 1704, laid the foundation for the science of optics. It explained phenomena like rainbows and provided a mechanistic understanding of how we perceive color. Modern applications, from fiber optics and laser technology to spectroscopy, which allows us to analyze the chemical composition of distant stars, all trace their lineage back to Newton's pioneering work with light and prisms. His work transformed light from an abstract phenomenon into a quantifiable, dissectable subject of scientific inquiry. The unifying force, universal gravitation. Perhaps Newton's most iconic and impactful discovery is his law of universal gravitation. Before Newton, the prevailing view was that celestial mechanics, the movement of planets and stars, was governed by one set of laws, while terrestrial mechanics, the movement of objects on Earth, was governed by another. Newton's genius was to synthesize these seemingly disparate phenomena under a single, elegant framework. The legendary story of the apple falling from the tree, whether entirely true or not, perfectly illustrates his epiphany. The same force that pulled the apple to the Earth also pulled the moon towards the Earth, keeping it in orbit, and similarly governed the planets around the sun. Newton articulated this in his groundbreaking work, Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, often simply called the Principia, published in 1687. His law states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This mathematical formulation, F equals gm1m2 over r squared, where g is the gravitational constant, revolutionized astronomy and physics. It explained planetary orbits, tides, and the paths of comets with unprecedented accuracy. This wasn't just a description, it was a prediction tool. Today, universal gravitation is fundamental to space exploration, guiding the trajectories of spacecraft, launching satellites, and understanding the dynamics of galaxies. While Einstein's theory of general relativity later offered a more refined understanding of gravity as the curvature of space-time, Newton's law remains incredibly accurate for most everyday phenomena and is still taught as the foundational principle for understanding gravity within our solar system and beyond. He truly unified the heavens and the earth. Laws of motion, the blueprint of mechanics. If universal gravitation provided the force, Newton's three laws of motion provided the blueprint for how that force, and indeed all forces, govern the movement of objects. These laws, also presented in the Principia, are the bedrock of classical mechanics and continue to be indispensable tools for understanding the physical world around us. Newton's first law, the law of inertia. It states that an object at rest will stay at rest, and an object in motion will stay in motion with the same speed and in the same direction, unless acted upon by an unbalanced force, acted upon by an unbalanced force. This concept, initially explored by Galileo, states that objects naturally resist changes to their state of motion. Think of a hockey puck sliding across ice. It travels a long distance because there's minimal friction, demonstrating its inertia. Newton's second law, force, mass, and acceleration. This is perhaps the most famous, F equals ma. It states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. This means a larger force produces greater acceleration, and a more massive object requires a greater force to achieve the same acceleration. This law is fundamental to understanding everything from how a car engine works to how a rocket lifts off. Newton's third law, action and reaction. For every action, there is an equal and opposite reaction. When you push against a wall, the wall pushes back on you with the same force. When a rocket expels hot gases downwards, the gases push the rocket upwards. This law explains propulsion, recoil, and how forces always occur in pairs. These three laws, deceptively simple, provide a comprehensive framework for analyzing the motion of objects, from subatomic particles to galaxies. Engineers use them to design vehicles and structures. Physicists use them to model complex systems, and even everyday observations like riding a bike or catching a ball are best understood through the lens of Newtonian mechanics. The reflecting telescope, a visionary design. Isaac Newton's contributions weren't confined to abstract theory and mathematics. He was also a skilled experimenter and inventor. One of his most significant practical innovations was the reflecting telescope, a design that addressed a critical flaw in the refracting telescopes of his time. Refracting telescopes, which use lenses, suffered from chromatic aberration, a phenomenon where different colors of light are focused at slightly different points, leading to fuzzy images with color fringes. This was a direct consequence of his own discoveries about the dispersion of light. Recognizing this problem, Newton conceived of a telescope that used mirrors instead of lenses to gather and focus light. He built his first working model in 1668, a compact instrument that dramatically improved image clarity by eliminating chromatic aberration. The primary mirror, typically parabolic, reflects light to a smaller secondary mirror, which then directs the light to the eyepiece. This design allowed for much larger apertures than was practical with lenses, meaning more light could be gathered, leading to brighter and more detailed images of celestial objects. Newton's reflecting telescope was a groundbreaking achievement. It demonstrated his practical ingenuity and his ability to apply theoretical understanding to solve real-world problems. Today, virtually all large astronomical telescopes, from the Hubble Space Telescope to the powerful ground-based observatories, are reflecting telescopes. These colossal instruments, some with primary mirrors tens of meters in diameter, are direct descendants of Newton's innovative design, allowing us to peer billions of light years into the cosmos and unravel the deepest mysteries of the universe. His invention literally expanded humanity's vision of the universe. Beyond physics, Newton's other pursuits. While Isaac Newton is rightfully celebrated for his monumental contributions to physics and mathematics, his intellectual curiosity was far broader than these fields alone. To categorize him solely as a physicist would be to miss a significant dimension of his complex personality and extensive work. Newton was also a devout theologian, spending an immense amount of time studying biblical prophecy and interpreting religious texts. He was particularly interested in chronologies and the history of ancient kingdoms, believing that Scripture held keys to understanding the past and future. Furthermore, Newton was deeply involved in alchemy, a proto-scientific pursuit that aimed to transmute base metals into gold, discover the elixir of life, and find a universal cure for disease. For many years, his alchemical manuscripts remained largely unexamined, but modern scholarship reveals that he conducted thousands of experiments, meticulously recording his procedures and observations. For Newton, alchemy was not necessarily distinct from his natural philosophy. It was another way of understanding the fundamental principles and transformations of matter. He was driven by a quest for hidden knowledge, seeking to uncover the secret workings of the universe through every available avenue. His role as Master of the Royal Mint, a position he held from 1699 until his death, also showcased his practical administrative skills. He was instrumental in reforming England's currency, effectively combating counterfeiting and stabilizing the economy. These diverse pursuits illustrate a mind that was relentlessly inquisitive, constantly seeking to understand the underlying order of the world, whether through mathematical laws, divine revelation, or chemical transformation. He was a polymath in the truest sense, a testament to an era when the boundaries between different fields of knowledge were far more fluid. The legacy endures. Newton in modern science. It's easy to relegate historical figures to textbooks, but Isaac Newton's influence is not merely historical, it is profoundly contemporary. His work forms the very bedrock upon which vast swathes of modern science and technology are built. Consider physics. Every student of mechanics still begins with Newton's laws of motion. When we calculate the trajectory of a projectile, design a roller coaster, or analyze the forces on an airplane, we are applying Newtonian principles. Even in advanced fields like astrophysics, while Einstein's relativity offers greater precision for extreme conditions, Newton's law of universal gravitation remains incredibly useful for understanding stellar dynamics and planetary orbits in most contexts. In mathematics, calculus, which Newton co-invented, is not just a subject taught in universities. It's the indispensable language of change used across engineering, economics, biology, computer science, and virtually every quantitative discipline. From optimizing supply chains to modeling neural networks, calculus provides the analytical power. His work on optics paved the way for modern photonics, laser technology, and the advanced cameras and imaging systems that are integral to medical diagnostics and digital communication. Even the scientific method itself, with its emphasis on rigorous observation, experimentation, and mathematical formulation, owes a significant debt to Newton's systematic approach to natural philosophy. Newton provided humanity with a powerful, coherent framework for understanding the physical universe, a deterministic worldview where phenomena could be predicted and explained through universal laws. While quantum mechanics and relativity have expanded and refined our understanding, they haven't invalidated Newton. Rather, they've shown the limits of his framework and where new physics takes over. His legacy is not just a collection of discoveries, but a testament to the power of human reason and the profound impact a single mind can have on the course of human knowledge. Standing on the shoulders of giants, a humble genius. In a letter to Robert Hooke in 1675, Isaac Newton famously wrote, "If I have seen further than others, it is by standing upon the shoulders of giants." This profound statement reveals not only Newton's humility, but also a deep understanding of the cumulative nature of scientific progress. He recognized that his own groundbreaking discoveries were not made in a vacuum, but were built upon the foundational work of predecessors like Galileo, Kepler, Descartes, and countless others who came before him. This adage perfectly encapsulates the scientific endeavor itself. Each generation of scientists builds upon the insights, theories, and experiments of those who paved the way. Newton's life and work serve as an enduring inspiration. He was a man of intense focus, relentless curiosity, and unparalleled analytical power. His ability to synthesize disparate observations into universal laws, to create new mathematical tools to describe dynamic phenomena, and to apply rigorous experimentation to unlock the secrets of light, profoundly altered humanity's understanding of the cosmos. He showed us that the universe is not a chaotic realm, but an orderly one, governed by elegant mathematical principles that are discoverable through careful observation and reasoned inquiry. From the simple fall of an apple to the majestic dance of galaxies, from the colors of a rainbow to the precise trajectories of spacecraft, Newton's fingerprints are everywhere. He didn't just discover facts, he provided a new way of seeing, a new methodology for understanding. His legacy is a constant reminder that the pursuit of knowledge is a continuous journey, one where each generation adds its own insights to the monumental structure built by those who came before. And in that spirit, we continue to stand on the shoulders of the giant that was Isaac Newton, ever striving to see further into the boundless mysteries of our universe.